Hey everyone, welcome to Science in Perspective. In this episode, I want to talk about the notion of smart intelligence, things that we are told in society that are smart but maybe are not so smart. So there is a video that was posted recently about some kids doing finger math. I don't know if you've ever seen this. I think it's pretty popular in China and India. I don't know how popular, but the basic idea is you would train, let's say, a child on a regular abacus, and then you would basically teach them how to visualize that abacus in their mind. And by visualizing the abacus in their mind, they can move their fingers. If you see them, they're just kind of doing this, moving their fingers, and they can come up with a calculation really quickly. I think they're just adding a bunch of numbers together, and they come up with that sum pretty quickly. So on one sense, it's pretty cool. I mean, it would be neat, I guess, to be able to do that as a bit of a parlor trick anyway, to, you have all these numbers and you can sum them probably faster than people can type them into a calculator. That's a pretty cool mental trick. There's another part that I kind of like about it, actually that I do really like about it, which is the visualization aspect, because I'm a huge proponent of mental visualization. I think that's at the core of a lot of the skills people should develop, especially as they relate to, understanding concepts and being able to memorize and recall those concepts and all that kind of stuff. So I'm a really big fan of developing mental imagery in your mind and getting good at that as a skill. What I don't like about this is the notion that this finger math, this visualized abacus, should be kind of seen as a precocious thing, seen as a smart thing that kids should be doing, or anybody in society should be doing. I don't think it's a good definition of smart. And I'm going to explain why I think that. Again, I like the visualization aspect, but there's lots of different things you can do for visualization, and low-level calculation like this is probably not one of them that's good to be doing. I mean, yes, you would be developing visualization skills in general, but I think there's better ways to do that. But more to the point, this low-level calculation stuff is just... I don't think it's a good definition of intelligence. I don't think kids should really be doing this. I think they need to raise the level of abstraction at which they operate, not just because that is more in line with how we've progressed as humanity. So in other words, don't do calculation. This is still going to be a lot slower than the majority of calculations you do in real life. It doesn't embrace the abstraction in mathematics, which is to understand the concepts that really underlie things. It's kind of a dumb calculation. And I'm not calling the people dumb. It's an amazing feat to be able to do this. Okay, there's that kind of smartness to it, but it's just not a good definition of smart in society. And we see this with other things, this kind of notion that low-level, detailed kind of analysis is what is supposed to be considered smart. And I don't think that's the case. I think that's problematic for society, and I don't think that's where we should be headed. Okay, so again, just using this as an example, there's lots of other examples, but this is called finger math. It's a visualization of an abacus, and you're just summing a bunch of numbers really, really quickly. It's more like a parlor trick. I don't see how that's going to be useful. Yes, it will help you mentally build some capabilities, but I just think really what I'm trying to say here is it's a bad definition of smart and it shouldn't be promoted. But I think people get impressed by that, right? People would speak against what I'm saying right now and easily say, well, that is really good intelligence, right? I mean, it's not easy to do. I bet you can't do that, right? And, that's not the point, right? I can't do that right now. I haven't trained myself. I believe I could train myself to do that. I think anybody could. I don't think they should be, because I don't think that's a good definition of smart. Okay? There's lots of other examples in the world and in society that I'll get into where you just talk about this kind of low-level analysis, and that's supposed to be what's intelligent. I don't think it is. Okay, so let's just start with kind of talking about math in general, right? Because I'm obviously not saying... Hopefully you appreciate that math is bad or something, that math is not good in general. I think it's got a lot of problems with it. I think the way that it's taught is awful, not just in this kind of sense, in North America as well. Most people have a gripe against math education for a good reason, and there are a lot of issues with it, but I'm not knocking math. You see math everywhere in society, right? So you see, we use it in artificial intelligence technologies when we set up the way that AI is going to make its predictions and the way that it knows the difference between what it's predicting and what the real value is. We have these objective functions. There's all kinds of probability in there. Obviously, mechanical engineering, really anything within the hard sciences and anything with engineering is going to use a pretty decent amount of mathematics, especially physics and chemistry on the hard sciences side, and then especially, building bridges, building rockets, building any kind of anything really, right? Because the math is going to allow you to frame the situation in kind of a cleaner, albeit approximate way that, allows you to balance forces, allows you to take a lot of things into account, and just puts it into a more controllable fashion, right? And this can get into decision making in life and all that kind of stuff, or at least that's how it will get promoted. So we see even in social sciences and that, and to some extent biology, you see a decent amount of mathematics. And yes, it doesn't go everywhere, right? Mathematics is not suitable for a lot of things. It's not going to explain why people fall in love. It's not going to explain actually quite a few things, because it can get pretty abused. It can be, people can assume that math can do more than it can. People can assume that something is rigorous because because it's mathematical, but that doesn't mean it's truly rigorous in the sense that it's mapping to reality. And I vehemently disagree with the notion that mathematics is the language of the universe. I think that gets tossed around a lot. But there is this notion, which I'll get into in a bit, that math is really good at explaining the way the world works. So it's not so much that math maps itself nicely to the world. What we've done is we've actually kind of created a world that maps itself to things like mathematics, right? If you take a look at the buildings, we make them as kind of Platonic shapes, and they're rectangular prisms or cuboids. Everything is a shape that doesn't really exist in nature to that extent, right? So because it's easier to think in terms of analysis and Platonics and mathematics, we tend to create the world like that. That doesn't mean that's how nature is. You don't see those kind of Platonic forms in nature. And this notion that math is doing a really good job at explaining nature is, I'm not saying it doesn't at all, but nowhere near to the extent at which it's promoted, right? And so you can take any kind of example. I mean, even just reasonably complex phenomena, right? You can kind of get a very extremely rough approximation of what something might be mathematically, but it just doesn't play out like that in the real world, not even close, right? You can use stock markets as an example. You can use, the dynamics of cities. You can apply math. People will do it. But there's a lot of assumptions there that math is actually telling you how it works, where at best, at a high level, it might really just be kind of characterizing the system. Okay, I began this talk saying, look, there's this finger math thing that people are doing, and I think a lot of people assume that that's pretty smart, but I don't think it's a good definition of smart, and I don't think it's the kind of thing we should be promoting in society. And then I said, hey, look, I'm not knocking math itself. You see math everywhere, and it gets used all the time. But what I want to move into now, which I've already alluded to, is why do we see it everywhere? Is it because it's super, super useful at explaining the world and making progress? I'm not saying straight up no to that. I mean, obviously there is some truth to that, but I don't think that's true anywhere near as much as people think. And a lot of it has to do with what I've already said, which I'll now call gamifying the world, right? We have really gamified the world, right? We have kind of put things down on a grid, and when you put things down on a grid, you can now count them. You can now do what is at the very foundation of mathematics, which is enumeration. All of mathematics, all of it, is fundamentally based on enumeration. And you can count things. You can put them in sets, right? The foundation of mathematics is sets, or you can do it as category theory if you want, but you're still counting. All of probability is about forming a ratio between a numerator and a denominator, right? And that's all about counting. Counting how many times something happens and putting over the how many things could happen in the full sample space, right? It doesn't matter what it is. It's all about counting, but you can only count things that are on a grid. So if you think about a city, right, we lay a city out as a grid. We put the streets perpendicular, or some are parallel, and let's say avenues and streets maybe are perpendicular to each other. Everything's on a grid, right? That's how we get around. That's not how you get around in the forest. That's not how you get around in the jungle. It's extremely artificial, actually. And I'm not saying it's not useful. I'm not saying it doesn't serve a purpose. When you get that many people together, they need to get from A to B. But again, a lot of that is pretty contrived. It wasn't really a necessity of civilization per se. It became a necessity because of the way we started structuring the world. And the way that we structured the world was very platonically, right? Was in line with the kinds of things you see in mathematics, the kinds of things you see in geometry, the kind of easier approximate narratives that we use to try to understand the world. Okay. That's why cities look the way they do. That's why we create things the way we do, right? You can create an airplane, a passenger jet, which is an amazing piece of innovation, but it's nowhere near as sophisticated as a bird. It'll go faster, but it'll only go faster in one direct line. It can't pivot on the spot. It can't adjust its velocity, can't adjust its trajectory. Any of that kind of stuff. It's nowhere near as sophisticated as what nature comes up with, right? As long as you only do that one thing, go from A to B in a perfectly straight line, then it's pretty impressive. As soon as you add any type of real-world complexity to that, the whole thing just becomes quite useless. Or a car, for example. A car is a great innovation. Look how fast we can go. We can go faster than a cheetah. car is nowhere near as sophisticated as a cheetah because you have to be on extremely flat roads, and those roads have to be straight. Again, we can't pivot, we can't turn on a dime, we can't adjust, we can't adapt with a car. It's an extremely limited piece of machinery. But as long as you create a world that is suitable to cars and suitable to planes, then those technologies can do what they do quite well. So the creation of the world that we've made is very gamified. I call it game, kind of like a chessboard, right? It's like we put a grid down and say, let's build things in grids. Let's build city blocks like that. Let's build machines that go on in straight lines. Any example you want to use. It's very, this goes here, this goes here. Because of that, math and things like math, and you can generalize that to just kind of analysis or kind of detailed oriented thinking, that kind of stuff becomes very prominent because it's useful in gamified situations. Okay. But that's not really nature. That really stands in contrast to nature. And so is math really useful in our world? Yes, that's a very different statement than math is really useful at explaining nature. I'm not saying it doesn't do it at all, but there's a big difference between, I'm going to use mathematics to set up an AI system, to create a rocket, to maybe design a city. There's a big difference between those things and saying I can use mathematics to explain the climate or to explain the market or to explain how a hummingbird flies or to explain really anything in nature. Okay. Now, physicists can get away with this more than anyone else because they explain simple systems. It might not look simple. If you walk into a physics classroom, you see a lot of mathematics on the chalkboard. It doesn't look very simple. That's because they're dealing with simple systems which reveal the core mechanisms behind how they work. As soon as you add any reasonable amount of complexity, that type of stuff isn't going to work very well. It's going to be extremely approximate. Physics can, and we're talking about degrees of approximation here, if you want to think about it in terms of approximation, right? You can say, well, all models are approximate. Well, yeah, but the one that explains a black hole is very, very different than one that explains how buffalo herds move through an area of the land. You can still do it, but those have almost nothing in common. The degree of approximation in the latter is gross compared to explaining something that's in the vacuum of space and has virtually no complexity. Black holes can have complexity, but not like anything that you would have on Earth, right? Which is just countless variables interacting, right? So I said at the beginning, we've got this finger math, we've got this low-level type of calculation stuff, and then I said, yes, math is everywhere, and it appears super, super useful, and in some sense, of course, is, but the sense in which it is useful is because we've gamified the world, which is not the same thing that it's not the same thing as saying that, math is the language of the universe. Well, if that were true, the universe would look gamified. The universe would look like how we build cities and how we build rockets and how we build planes, but they don't. The plane barely looks anything like a bird, really, other than on just extremely gross approximate level. Cities don't look like the jungle at all, right? So no, I don't think mathematics and detailed analysis is the language of the world. I don't think that makes sense. Not knocking math, it just has its place. And you can use math in better ways, actually. So you don't have to get rid of math, right? And I've talked about this in other episodes and stuff. If you raise the level at which you operate of mathematics, like in the purely, let's say, abstract sense, more in the way a pure mathematician would, actually. The applied mathematician uses it in kind of that low-level way. The pure mathematician uses it in a very abstract way, where they just they don't really do calculations. Pure mathematicians don't really do calculations. They actually just make logical arguments with definitions, and those definitions are mathematical definitions. It's a very abstract, high-level way of using math, which is, to me, a much more appropriate way to actually define nature. So ironically, I think pure mathematics is actually far more applicable than applied mathematics because of the way the paradigm has been set up. Okay, that's kind of going a little bit off topic, but I just want to give some, so I want to tell you, that I'm not arguing against math itself, but the way that it is applied and just analysis in general. Okay, another point I want to make is that, our education system kind of vilifies memory, right? So for example, you hear this a lot, like, don't just remember, make sure you learn. It's kind of a dumb thing to say because the biggest part of learning is memory, right? Like if you've learned something, it's because you've remembered the concepts, you've internalized the information, and you can recall it. What people are really saying is that, okay, but don't memorize verbatim. Like don't memorize all the details and not understand what those details synthesize into, which is correct. Okay. But that's how you should be using memory, is to memorize the abstract, to memorize the synthesis, right? The analysis, the low-level detailed stuff is not particularly useful in the real world. Real world, particularly the natural world, right? If you're interacting with individuals, if you're getting into negotiations, if you have to find a job, if you have to find a partner, if you have to build your career, and quite frankly, even if you want to create technologies, one, because technologies are changing and they're becoming far more abstract than they used to be, right? You used to do a lot of low-level stuff. Now the level of abstraction is much higher. So the details don't matter like they used to. AI is a perfect example of this, right? AI technology is not about details. It's not rules-based software, right? Symbolic AI has failed, which would be the AI you try to create when you do low-level facts, basically, that you bake into the system. So if this happens, then you do this. It's all fully deterministic, right? That does not work. You have to let go. You have to let the machine do its own thing for millions and millions of iterations until it converges on a solution. It's very non-detailed. It's very non-analysis based. It's not rules based, right? It's far more abstract. It's far more genuine complexity. Okay. So this kind of, well, don't memorize, you should really learn. But what people mean by that is you should really learn all these isolated facts in the textbook and just do a lot of the details, devil's in the details. But that's a dumb way to do things now, right? It really is, because things are far more abstract now and they're much higher level. And that actually brings us full circle to the way humans are supposed to be navigating the complexities of their world, because we evolved in a complex world. We didn't evolve for a gamified world. The simplistic streets and grids and A to B airplanes, that's super, super simplistic. And that's not genuine. There are no genuine hard problems in that type of technology, because those technologies are gamified. Categorically hard problems exist in nature, like pattern recognition, right? Things that detailed analysis by definition cannot solve. Okay. So why am I talking about like kind of vilifying memory and saying, well, that's not learning. It's actually the details. Well, no, details are not learning, because they're disconnected from what matters and how nature works. And today becoming even how technology works. So memory is better. Now, but the point is not to memorize the details. Memorize the abstractions, memorize the high-level concepts, internalize what actually matters. Kind of like the pure mathematicians take, where they're not really running calculations. Once you graduate beyond a point of kind of grade school and high school math, and even a lot of the applied math, and you get into pure math. Pure math is about abstractions and logical arguments, which is far more abstract. That's more realistic, because nature operates in abstractions. It doesn't the details get washed out, right? Complex systems, which is everything in nature, wash out details. The details are only there because they subsume to higher levels of abstraction. Okay. So I said at the beginning, we got this finger math and it's all low-level calculation. I said, that's not a good definition of smart. Then I said, okay, yes, math is everywhere. First point. Second point, it's only everywhere because we live in a gamified world, which nature is not. Third point, basically, I'm just saying that we're moving closer to nature. We're building increasingly complex things. And because of that low-level detailed analysis is actually a pretty dumb way to go about defining smart. It's not a smart thing. People who, and you see this everywhere, right? Like if you try to bring hard analysis to your life, you're going to fail. It doesn't work. It never has worked. If you're going to try to win a negotiation because you think you can do it with game theory, it's not going to happen. Okay, it's called game theory because it's a game. And real life, is not a game. If it's in a super gamified setting, yeah, game theory will work. Real world is not a gamified setting. So the core mechanism that I'm talking about here is, what I call in my book, progress by abstraction. And if you look at progress, there's all kind of ways you could talk about human progress, but I would argue the number one way is by abstraction, not by figuring things out at the low level, not by, we like to say that, like, oh, well, somebody came along and they really figured out how this worked. At the end of the day, it's because each generation operates at a higher level of abstraction than the previous generation, right? Computing is a good example of this. We started with machine code, very low-level programming languages. Then we got into scripting, up, all the way into AI, right? Where basically we're getting to the point where maybe you don't even need to write code anymore. We're not there, but the abstraction level keeps increasing. But that's true of everything, right? Even the stone axe compared to a better tool. You'll notice in any tool that we create, tooling being very much the defining quality of humanity, right? We use tools. Progress is really because the abstraction level is increasing. We subsume we hide more of the details beneath the surface and we operate at a higher and higher level. And eventually those details are not even part of the system. They pretty much get washed out, or if they can still be there, but there's nothing left to figure out about them, right? There's nothing left to figure out. We've got all of those low-level things packaged into higher-level modules, and now what it means to build is just to combine those high-level modules. You see that in every aspect of technology. You won't find an exception to that. People might be choosing to do the low-level details, like finger math, but that doesn't mean they should be doing it, right? So it's all about progress by abstraction. And I think computing is a good example, but you can see this anywhere where you keep raising. So I just wanted to bring this example up in this episode because there's a science behind this. It looks smart, but if you have an appreciation of how progress happens, if you have an appreciation of the core mechanism of progress by abstraction, right, which is to truly scientifically understand how progress happens and how hard problems are actually solved, then I don't think this is a smart thing. And this kind of doesn't just have to be finger math. I don't believe in starting with really isolated fundamentals and then building your way up. I think you should jump into real world challenges, and then you'll appreciate why those fundamentals mean something, which is of course how fundamentals were discovered in the first place, right? You don't make progress because you take little pieces and you combine them. You make progress because you jump into the combined situation, and then out of that you find pieces that seem to make the most sense and that are the most important, right? The problem with math education and even science education, maybe all education, right, is that once the fundamentals have been discovered, then we just teach the fundamentals as if students are going to bring those fundamentals together and magically combine them to create something higher level later on. But that's the exact wrong direction, right? Isolated fundamentals don't have meaning, right? Just like the words in a dictionary don't have meaning, they have definitions. They don't have meaning until you take the word and you embed it in a sentence, which gets embedded in a paragraph. That's what gives meaning to something. You need to learn in context, okay? So I just wanted to use that as an example. You can go check these videos out. It's cool. Don't get me wrong. It's a really neat parlor trick. I mean, it must take a lot of training to do calculations that fast in your head. And I do like the mental visualization aspect of it because mental visualization is huge. But use mental visualization for something smarter than doing low-level calculations, which just don't map to reality and are not going to be useful, and I don't think are a good way to train yourself for much of anything. Navigating life, even doing science and technology, because again, science and technology is changing. It's becoming more abstract. It's operating at a higher level. The low level stuff is going away. It should go away. It was never how our brains were supposed to be figuring out problems and solving categorically hard problems. You're not going to calculate your way through a forest. You're not going to calculate your way into recognizing someone's face, into negotiating, into finding a partner, into building a life for yourself, whatever it is. Into building the next round of rockets, it should be less and less about calculation, right? Because those details should be subsumed into higher level components, which now get blended into the next level. That's how you make progress. Okay, that is it for this episode. Thanks so much for listening, and everyone who is watching. Hey, if you would like more of this content, you can become a premium member over at scienceinperspective.com. You can also check out patreon.com/Sean McClure. The links are in the description. I do techniques and mindset videos, help you to think more like a scientist in your everyday life and in your creative projects, whatever it is. I just go over techniques the last one I did was on Bayesian updating. So you can think about how to update your priors more effectively conceptually. It's a good model to kind of be a little bit more scientific in how you go about things. It's good to learn these techniques. And then mindsets, kind of the habits and lenses with which, the scientific mind might look at things. I think that can be really helpful, help you avoid some pitfalls in life that maybe are there because you're just, you have never been exposed to this kind of more objective way of looking at the world. So I think that's worthwhile. So anyways, go ahead and check those links out in the description. Again, thanks everyone for listening. And for those of you who are watching, until next time, take care.